Okay, so this is integrated to 2.2.2 similarity. All right, similar polygons. So this should hopefully sound familiar from a couple of years ago. We have congruent corresponding angles, but we also have corresponding side lengths that are proportional. So it's the whole idea of being able to find a ratio between them. So in this first example, we're being told that the triangles are similar. All right, we need to find the ratio of similarity. The ratio of similarity is that fraction that relates the sides. If these are truly similar, then we need to make sure that the ratio is consistent the entire time. So I'm going to take a look back at the picture. I'm going to match up the sides that should go together. So like small with small, medium with medium, large with large. So the small is the 2 and the 5. So I'm going to go ahead and write the ratio. I am choosing to go small triangle to large triangle. You could go large triangle to small triangle. Just be consistent with it. Then we also have medium with medium. Let's see, that's going to be 4 and 10. So I'll write 4 over 10. Again, be consistent. So I went small to large. And then the last one that I'm going to do is the 5 to 12.5. Now, if we go through and we simplify each one of these fractions, if this is truly similar, then they need to be the same. Okay, well, 2/5 can't be simplified, but 4/10 is 2/5. And then if we check this in our calculator, that is also 2/5. So I'm going to say that our ratio of similarity is going to be 2/5. In order for the triangles to actually be similar, those ratios must be the same. Okay, so then a little bit more review of proportion, or this whole idea of ratio stuff. So a proportion, this is an equation with two equivalent ratios. So if we take a look at this example on the left-hand side, still doing the same thing that we had done before, we know, or just did in the previous question, we know that small goes with small. So we're going to put 6 over 18. We're going to know that, well, large maybe, I think it looks like the longest side in here is going to be 8 over 24. So the ratio with the two. If these are similar, then they need to be the same. Okay, which they are. So we're going to use this notion of, okay, maybe I know the ratio comparison of two of the sides, but I need to be able to use that ratio to help me find something that I'm missing. So if we take a look at this example over here, following kind of the same layout, we're going to put the 6 and the x together. Now this ratio may not be the same, which is okay. So we'll have 6 over x, and then we're going to compare the other ones together, so the 8 and the 20. So if these really are similar to each other, then these two fractions must be equal, kind of like the previous problem. And then to solve this, we're going to go ahead and cross multiply. So I'll take the 6 and the 20, and I'll multiply those together, equals, and then I'll take the 8 and the x and multiply those together. Beautiful part about cross multiplication is the fractions disappear. Go ahead and divide by 8. And then I think if we divide this, I think we just get 15. And that's going to be our answer. So that x is going to be equal to 15 in this case. Okay. Moving on to 2-59 from the textbook. We're being told that the triangle ABC is dilated through the point A to create a B prime C prime. Okay, so the smaller triangle. Why are the two triangles similar? Well, that's because of its dilation. So, since a dilation created the smaller triangle. And then we want to go ahead and write the statement. All right, so we know, let's go ahead and take a look at these triangles. So I'm going to use blue to color code the original triangle. So no prime marks or tick marks on this. So I'm going to call that triangle ABC. And we're going to say that this is similar to, so be careful with those symbols. This is similar to, and we're going to use that small triangle. So A, B prime, C prime. So I just want to kind of follow the order that I had already set up on the other one. So triangle A, B prime, C prime. Okay. I decided to redraw the triangles or redraw the diagrams as two separate triangles. Okay, this can be super beneficial for some people. So let's go ahead and color code this again. So the small triangle, so the new one that was created, I already color coded red. So let's stick with that. And then the original large triangle was blue. And we'll stick with that. Okay, so it can be beneficial for some people to redraw these. Highly recommend it. We want to write a proportion for solving for x using the corresponding sides. Okay, so taking a look at the large picture and taking a look at the two separated pictures, I know that from A to B, and I can look back at the name, I know that from A to B should be similar to, I don't want to say equal because they're not. There needs to be a ratio comparison as it is from A prime to A to B prime. So I know AB, and AB is 4, should match up with A to B prime. Oh, excuse me, A to B was 10. Keep wanting to go small triangle to big triangle. So 10 over 4. Okay, so that is going to be AB over AB prime. Okay, now what's nice about this ratio that's already set up is there are no variables in this. I'm going to go ahead and set up the other ratios as well. So AB was the first one I did, so let's do AC. Let's stick with the larger triangle. And AC is going to be x plus 9. And then we're going to do A to C prime. Well, A to C prime was x. Okay, we know that these are similar because of the dilation, which means these two ratios had better be the same. So let's go ahead and set these equal to each other. So 10 over 4 is equal to x plus 9 over x. And then we're going to go ahead and solve. So we're going to cross multiply here. So that's going to give me 10x equals, just be careful here and make sure that you distribute. So we're going to do 4 times x plus 9. So 10x is equal to 4x plus 36. Move your 4x to the other side, and then divide. So it looks like x is going to be equal to 6. Solve for x. All right, there we go. Okay, so we set up our proportion. So that's going to be the x plus 9 over x plus equals the 10 over 4. Then we solved it, and we got x is equal to 6. Write a different proportion and solve. Okay, so there are a couple of ways that you could do this. What we did first was we identified large and small triangles that looked like they matched up. So the 10 and the 4. Then we matched up the x plus 9 and the x. So that was one way to do it. Another way to do it is that you can actually go from units inside a single triangle to units inside the other triangle. Just be careful. So I know that I can put 4 over x. So 4 over x equals, and then just again, be careful. Notice that I went yellow over blue. So I could do yellow over blue, 10 over x plus 9. It's another proportion. It should give you the exact same answer. So let's make sure here. We have 4 times x plus 9 equals 10 times x. Yeah, you see you get the exact same question or exact same equation that pops up from stemming from a completely different proportion, which is totally fine. We still get x equals 6. How long is AC? All right, so AC was identified as x plus 9. So I know that AC was identified as x plus 9. So go ahead and plug in your x. So it looks like it's going to be 15. And I believe that this said that they're all in centimeters. Yeah, so that's going to be centimeters. Okay, so then we should be able to find AC prime. Okay, well, we could have found that first. Could have done AC prime. That was just x, and x was 6. So that's 6 centimeters. All right, what's the ratio of the original BC to its image B prime C prime? Okay, well, the ratios have to be consistent the entire way through. So if we take a look back, I'm going to go ahead and use a pink box. If we go back and take a look at B, where we first set up the ratios, you want to find the one that only has numbers in it, because that ratio is the one that is going to match for all of the sides that look like they compare, which in this case is going to be 10 over 4. You could simplify it to 5 over 2. You get the same thing. So the relationship, okay, let's be smart about this. We want to do BC to its image. So that means we want to do BC over B prime C prime. Now, just remember taking a look at the picture, since I keep falling into the habit of thinking that the larger one is the new one, which it isn't. We know that BC comes from the original shape, so that would be the 10, the larger measurement, and then the B prime C prime would be 4. Again, you can simplify this to 5 halves. And explain, well, the reason why I know that is because the ratio on the other side lengths was 10/4, and if this is truly similar, which it is because of the dilation, the ratios have to be the same. What's the relationship between those two in the original diagram? Well, there's a lot that we can say here. So if we know that these two triangles are in fact similar, which they are, then I know that all of the corresponding angles inside the triangles are going to have to be congruent, since that's one of the requirements for similarity. So I know that looking back at my picture, I know that where A, B prime, C prime, so that angle in that red corner is going to be congruent to A, B, C, that angle. Additionally, I know that AC prime B prime is going to be congruent to ACB. Okay, so if I see measurements like that and it looks like corresponding angles are matching, well, if corresponding angles are matching, then I'm led to believe that these two line segments are actually going to be parallel to each other. So I'm going to say parallel. And I think that finishes the notes for this.